Hi everybody, Dr. White here with section 2.5 on the hypergeometric distributions. So imagine that you've got an urn, and inside that urn are some balls. Some of them are black, in one of them are black. Some of them are white, in two of them are white. Okay, the total number of balls, n1 plus n2, shall be called capital N for short. Now, our plan is to draw little n balls at random without replacement from that urn. Okay, so we do not put a ball back in after we've drawn it. And we want to create a little random variable to go with this experiment. Let's let capital X be the number of black balls that are drawn. So we're counting the number of black balls in our n draws. So we'd like to do things like find the probability mass function, the probability capital X equals little x. So that'll be a non-zero probability for if x satisfies certain conditions. Clearly x needs to be less than or equal to the number of balls that you draw. You can't get more black balls than how many balls you draw. You also can't get more black balls than there are in the urn. N minus x is the number of white balls you're going to draw, and you can't get more than n2 of those because there's only n2 in the urn. But within those ranges, there's going to be some non-zero chance of getting x black balls. So what is it? Well, because you're drawing randomly, then all orderings of black and white balls or of n black and white balls are equally likely. So all we need to do is count up the number of ways to pick x black balls and n minus x white balls and divide that by the number of ways to pick any n balls. So the top is clearly a multiplication principle problem. The number of ways to pick x black balls would be the number of ways to pick x things out of the n1 black balls that are available. And then the number of ways to pick n minus x white balls would be n2 choose n minus x. You multiply those together. And then the number of ways to pick little n balls out of capital N balls is capital N choose little n. So there it is. Pretty simple and intuitive formula for the probability mass function. So a random variable that has this distribution is said to be of the hypergeometric family, hyper for short. The numbers that determine it are the number of black balls in the urn, n1, the number of white balls in the urn, n2, and the number of little n of balls you're going to draw at random without replacement. So I'll just refer you to the textbook for the detailed calculations on the expected value and the variance of hypergeometric random variables. You don't use the moment generating function technique. The moment generating function doesn't have a particular convenient form. But you can use various little summation tricks that are described in detail in the book. And what you find is the expected value, the expected number of black balls is the number of draws times the proportion of balls in the urn that are black. Okay. And the variance reminds you a lot of a binomial random variable. N times the proportion that are black times the proportion that are white. 1 minus the proportion that are black. N times p times 1 minus p. Feels like a binomial. But there's this extra factor at the end as well. The number of balls in the urn, the population, minus the number of balls you pick out, the sample size, over the population minus 1. That little factor there is called the correction factor, because the thing is like almost binomial, but you got to multiply by this correction factor. As a matter of fact, hypergeometric random variables really look and behave a lot like binomial random variables, um, as long as the population size, the number of things in the urn, is a lot bigger than the sample size that's pulling out of the urn. And the reason for that is, like, imagine what happens when you pick from the urn. Like say that your first draw is of a black ball. So what about that second draw? What would be your chance of drawing a black on draw 2? Would it be the same as the chance on draw 1? No, because on draw 1 your chances were n1 over n. You know, on draw 2 you're looking at a different urn because you haven't replaced the black ball you've drawn. There's n minus 1 black balls left. There's n1 minus 1 black balls left. N minus 1 balls in the urn left. That fraction is not the same as n1 over n. But if n's real big, then it's about the same as n1 over n. So your chances for a black ball don't vary much from draw to draw with what you've already drawn before. So the actual correct fractions that you would be using to compute probabilities for getting a black ball on this draw and a white ball on this draw and so on, they're actually pretty close to the same values. You know, they're pretty close to the p n1 over n and the q n2 over n. And so that's why these hypergeometrics are really going to have probability mass functions that look a lot like binomials, as long as the population size capital N is big. We'll tend to do our hypergeometric computations in R, so let me step over to sign in. It's getting to me. Here it is. And we've got some slides to help us out. Head to the common folder, Dr. White stuff, Math 331 slides, Section 2.5 slides, HTML, view in the web browser. Here they come. So computing the hypergeometric probabilities. Let's give ourselves an example to work with. Let's say you pick 20 balls at random without replacement from an urn where 100 of the balls in the urn are black and 100 of the balls in the urn are white. And let's let X be the number of black balls you get. So you set yourself up a hypergeometric random variable where the n1 parameter is 100, the n2 parameter is 100, and the little n parameter is 20. And say you want to find what's the chance of 12 black balls in the 20 that you picked out. You could certainly just use the probability mass function formula. 100 choose 12, 100 choose 8, 200 choose 20. And so you could do that in R with this very easy command. We know the choose function in R, no problem. You get about 12% as your answer. But you can also just use a function built to find probabilities for hypergeometrics. dhyper will find the probability for hypergeometric to be any specific value you ask for. So if you want to find the probability of 12 black balls, put a 12 here. Then you got to say how many black balls are in the urn. And that's done with a parameter called m in this function. You got to say how many white balls are in the urn, and that's done with a parameter called n in this function. You got to say how many balls you're drawing out without replacement, and that's done with a parameter called k. So like it's really going to be really hard to remember those parameter names. You'll probably have to do like get help on dhyper every time you use it for a while. Or just remember to use things in the right order. the number you want, number of blacks, number of whites, number of draws. So if you wanted a cumulative probability, you can do p hyper. So for like probability that the number of black balls drawn is less than or equal to 13, do p hyper, put in the 13, number of blacks in the urn, number of whites in the urn, number of draws, and you can see there's a pretty high chance of getting less than or equal to 13. Hey, let's take another look back at that Bayes theorem problem about the flu vaccines, okay? So let's restate the problem. You got a hospital that gets flu vaccines from 3 companies. 40% of its shipments come from company A, 50% from company B, and 10% from company C. And it knows something about the ineffectiveness rate of the little vials of flu vaccine that it gets from these companies. 3% from company A are bad, 2% from company B, 5% from company C. And the hospital tests 5 vials from any shipment that it gets. And its plan is if at least one of the 5 vials out of the many vials in the shipment are bad, then it's going to reject the whole shipment, send it back to the company. And our problem was like, what's the probability, if you reject a shipment, what's the probability that the shipment came from company C? And remember that we set up Bayes' theorem to handle this problem. And the meat of the problem was these conditional probabilities, like the probability of rejecting a shipment if it came from company C. Similarly for company A, company B as well. And to find those conditional probabilities, we modeled the process of testing 5 vials out of the shipment as binomial random variables. So like we said, if the shipment came from company A, the number of vials that were ineffective, not rejected, ineffective, would be a binomial random variable with 5 trials chance of success 0.03. And same for the, other counts that come from tests from other companies. But, really the number of ineffective vials in 5 that you test is not actually a binomial random variable, because it's not really built on 5 independent Bernoulli trials. They lack independence because, like, if the first vial you pull out is ineffective, then you've changed the proportion of ineffective vials that's remaining in the shipment. And so you're changing the chance of getting an ineffective vial on your second try, and so on. What you really have got here is the hypergeometric situation, not the binomial one. So let's see if we can set ourselves up a little bit better. We'll have to add some information into the problem to proceed. So why don't I'll just make an assumption that say each shipment contains 1,000 vaccines. Okay. So a shipment from company A, where it's known that 3% are defective, we can just sort of make a guess that such shipments would have 30 defective, because that's 3% of 1,000, 970 good vials. A shipment from company B, you can just estimate, would have 20 defective and 980 good, and so on for company C, 50 defective, because 5% of 1,000 is 50. And so making those assumptions about the shipments from the 3 companies, you can do the same basic work as before. The probability of rejecting, given that the shipment comes from company A, is the probability of 1 or more bad. That's 1 minus the probability of no bad. But we're not going to do D by known. We're going to do something else. Now, when we did d by known, then we remember we got about like 17.78%. The way we're going to do it is with d hyper, because that's actually the random variable going on is hypergeometric. And so, like, the chance of rejecting if it comes from A will be 1 minus the chance of 0 bads when your urn contains 30 bads and 970 goods, and you're pulling out 5 without replacement. And similarly for B and C. And so then when we head to Bayes' theorem down here, we get, almost the same thing. Yeah, that's like same to, it's the same to 4 decimal place. I mean, they only start differing in the 5th decimal place. There's scarcely any difference. But then we think, oh, that's right. You know, when the population size is really big compared to how many you're sampling, hypergeometrics are supposed to behave a lot like binomials anyway. And so no surprise that your answer is just about the same. Still, good conceptual exercise to go through. So that's all I've got for you on hypergeometrics. See you soon with some more exciting discrete random variables.